Hey there, and welcome to your next lesson on higher level mathematics. So we're continuing with numbers, and today we're looking at approximations. So far, whether we're looking with whole numbers or proportions like fractions and decimals and things like that, we've always worked with doing exact calculations. Whereas today we're looking at how do we find the approximate answer to a question and why would we want to do that? So let's look first at the lesson plan. So only three sections for today. We've got rounding, which is how we basically simplify numbers at the cost of some uh, accuracy. Then how we can then use that to estimate a calculation. We make it simpler. We estimate, it allows us to estimate it. And then what kind of errors do we get as a result of that? And what error bounds are we going to get? So what range of answers would the true answer be? uh, uh, as a result of this rounding that's occurred, and how do we deal with that? So that's what we're going to be looking at. So let's take a look at rounding first. So how do we round numbers? So let's first of all, like I mentioned, it's a way to simplify complex calculations, particularly say for math we're doing on paper or mental math. Say if you're out at the shop and you're comparing prices of different products and you don't want to get the exact value, you just want to get a rough value. That is one example of why we would use rounding. Makes numbers easier to read, like we saw before with percentages is a handy way of expressing proportions if you're presenting to someone. Again, rounding is another way, another thing we might do to if we had something to many decimal places, we don't need so many. We could just shorten it down and make it easier to read. Um, and yeah, generally avoid being over precise. Sometimes you might not need all those decimal places, you might only need two, for example, or even to make them more realistic. Say if you're dealing with something that is an integer value, but say if you calculated an average number of people who partake in a particular activity and the number comes out to say 11.6 or something like that, obviously you can't have zero point 0.6 of a person. So we would round that to the nearest whole number, for example. So these are some of the uses of why we round. So let's take a look at how we actually round numbers. Um, so we can just look at this visually. First of all, we've got a number line here. And say if we had the number 12.3 and we want to round that number is going to be here. If you might be able to see each square along that line is going to be zero point 0.1. So between 12 and 12.5, we can see 12.3 is going to go there. And so if we're rounding, say, to the nearest whole number here, you can see either side of this number, we've got 12 and 13. Those are our two numbers either side, and you can see which one's closer. It's the 12. And so that's how we round the number. We're rounded to the nearest whole number in this case. It all depends what you're rounding to, but in this case, yeah, it's going to be 12. And we take another example, like 10.8, you can see that would be here. And if we round that, you see that's going to round up to 11 there, because it's closer to 11 than it is 10. And then a final example is say if you have something like this where it's dead in the middle, it's at 12.5, that's exactly halfway between 12 and 13. What do we do in that case? Well, here we have, what is just basically like a mathematical convention. We always round up in this case, even though it's equal distance to both. That's the way we essentially all agree to do it. And in that way, we understand each other's work and like how we've rounded things if we all, follow essentially the same rules. So, if we take an example of trying to multiply these numbers, like say 12.3 times 10.8, that could be a little bit complicated to do in your head, but you see here 12 times 11 is very straightforward. And if you know your 12 times tables well, you see that's going to be 132. And the true value we can see is 132.84. So we're actually not too far off there, just 0.84 off. Um, right, so now let's look at a different type of round. So it was rounded to a particular place value there, like it was rounded to units. And you see each place value is basically a multiple of 10, whether you're doing units, tens, hundreds, thousands, and so on, or you're going the other direction where you've got tenths, hundredths, thousandths, and so on and so forth down to the right at the decimal point. They're all basically powers of 10. And so rounding to the nearest like particular decimal place is essentially rounding to a power of 10. But say if we wanted to take this number and we want to round not to a power of 10, we're rounding to the nearest 500. what would that be? Well, again, let's put it on our number line here. So we've got a new number line, and you can see either side of that number, we have two multiples of 500, 6,000 and 6,500. And you can see the one we're closest to there is 6,500. And we can take another example like this. Um, 7,752. Right. So that looks a lot more central. It's hard to tell exactly which way that's going to go. How would we work that out? So in this case, what we do is we need to look. We can see each multiple of 500 either side of this number is 7,500 or 8,000. And we work out the midpoint. So the number in the middle of that is going to be 7,750 because you can see half of 500 is 250. If you add that on to 7,500, you get 7,750. That's the number right in the middle. And you can see the number we've got here, 7,752, is just ever so slightly higher than that. So it's actually going to round up to 8,000. That's just slightly closer. So see, sometimes this visual method won't always work unless it's very clearly going to go one way or the other. You need to be able to look at the number and you see, where is the midpoint and then where is your number relative to that midpoint. If it's to the left, then it's going to round down. If it's to the right, it's going to round up. You get an example like this. Again, it's quite straightforward. We can easily see that's going to round down to 7,500. That one's clearly closer than the 8,000. So that's what we have to do there when we're not dealing with a decimal place. We're dealing with rounding to a specific number. And you need to be aware of that. So we're looking at our multiples of 500 there. You see the midpoints between those multiples of 500. And then you compare which side of that midpoint is your number on. That will determine whether it goes up or down. Now, let's take a look at say one that fits that last criteria, a number being overly precise. Like you might have some measurement that comes out really precise like this, but we don't need it that precise. We just need two decimal places. How do we round that to two decimal places? Well, the number on the number line is right here, and we want to see which way that's going to round. Well, looking at the number line, you can see it's going to round up to 1.06 as opposed to 1.05. That one's further away. But say if we didn't have a number line like this, or perhaps it might not be practical to use that, you can see here we can draw a line past that second decimal point, or whatever decimal point. You might be doing 4 decimal places, 1 decimal place, whatever. Here we're doing 2 decimal places. So we draw that line after the second decimal place, and we look at the number coming after it, and that will then determine whether or not that 5 is going to stay at 5, or will it round up to a 0.06. In this case, yeah, it will go up to 1.06 because that next number is greater than 5. So if we're looking at the decimal places here, the next digit, being a 5 indicates being right in the middle. Less than 5 means it's going to be, under the midpoint. Greater than 5 means it's going to be over the midpoint. And so, we can look at that next digit and it'll tell us which way to round. Same thing with this number here. We don't even have to look at the number line. We can just see 1.08. Next digit is a 1. So it's going to be closer to 1.08 than 1.09. So it rounds down like that. And finally, one like this. Again, you might get like a bit more of a borderline case like this where it looks like it's right in the middle, 1.065, halfway between 1.06 and 1.07. But you look at the number there, the number after the 6 is a 4, 4999. Like it's very, very close to 1.065, but ever so slightly under. So it will round down to 1.06. So that's how we deal with rounding. We have another example of rounding, what's known as significant figures as opposed to decimal places, or rounding to a particular number, like, round to nearest 500, like what we saw before. So say if this works really well when you're dealing with very small numbers like this. So 0.000, a whole bunch of zeros, and then we get some non-zero digits. If we rounded to a few decimal places, like say 4 decimal places here, you see that's basically just going to be 0. Or even if I did 7 decimal places, it's still just going to be 0 because we don't hit a non-zero number. And so rounding, it would come out to 0, even though it's not 0. It's just a really small number. And so in these cases, say if you're dealing with many very small numbers, there might be different sizes, and you don't know what, rounding to one, a particular number of decimal places could cause these kinds of problems. what we do is instead we round to significant figures, where it's basically all those zeros right in front, you ignore all of them, you get to the first non-zero number, which is a 3 here, and then you essentially start counting decimal places from that point. So here we count 3, 4, that's your two significant figures, and then we stop there. And the 4 stays as a 4 because you see the next digit is a 0. So the 4 is not going to round up to a 5, it'll stay as 4. But an important thing to note here is, say if you have 4 significant figures like this, you see it's 3409, not 3408.6, say, because that O, that 0 after the 4 is now a significant figure. You don't skip over that one. You skip over all the leading zeros until you get to the first non-zero number, and then from there, every number is now considered a significant figure, and you don't skip over any of them. You just, so in this case, we count up 4 figures. So we get 3408, but you see the next digit is a 5, so that 8 rounds up to a 9. So we get 3409 here. So that's how significant figures work. So very much the same thing, except it's how you deal with these really small numbers. You skip over all those zeros first, which are called, insignificant figures, to the first then significant figure, which is basically one that's not 0. And then you just do the same thing as you have been doing from there. Right, so that's rounding. Now let's see how we use rounding to estimate calculations. So we could take a few examples, like say this one here, and you can see each number will round down, and we could just do 12 times 13, which is a much easier calculation to do, especially if it's in your head or something like that. Another one like here, you see they're both going to round up, and we can add them together in this addition. Another example, multiplication, you can see one's going to round up, one's going to round down. You get 20 times 11, which is, again, easier calculation to do than these decimals. So imagine, if this was a calculation you're trying to do in your head, you could just do this way simpler, way faster by simplifying it like this. Now, if we look at this and try and think, how accurate are these estimations? And have we overestimated, as in we've got a value that's bigger than what the true value is, or have we underestimated, as in we've got a value less than what the true value is? So we can do that by looking at how we've rounded each number. So 12.1, rounding to the nearest number is rounding it down to 12. And same thing with 13.2, we've rounded that down to 13. So we've got two numbers that we're trying to multiply together. We've rounded them, and by rounding them, we've brought both the numbers down. So we're now multiplying together two numbers that are both smaller than the true value. So what that means is this is going to be an underestimate. Because imagine if you had two numbers you're multiplying together, say if I make both numbers slightly smaller and then multiply those instead, it's going to produce a smaller answer, isn't it? So this is underestimate. But probably still reasonably accurate because we haven't rounded too far, only like 0.1, 0.2, but they've both gone down. So we know that the true value is at least 156. The next one, you can see the 66.7 has been rounded up, 65.9 has been rounded up as well. It's a little bit more of a rounding, rounded by 0.3 there on the 66.7. So it might be a bit less accurate. In this case, we're just adding rather than multiplying. So the errors don't seem to amplify so much when you're adding. When you're multiplying, the errors can really grow quite fast. So these are certain things that can affect the errors. But in this case, you see they're both being rounded up. So if we have two numbers that we're adding together and we make both numbers slightly bigger, you understand with addition, the final answer is then also going to be bigger. And so this is an overestimate. We know the true number is actually going to be a little bit less than 113. And with the final one is a bit more of a trickier case because you see here we've got one that's going up, like 19.9 rounded up to 20, whereas 11.4 rounded down to 11. And we've got a bit of a bigger difference now. The 11.4, we've rounded down, 0.4, a bit of a more significant round in there. But you see one is going up and one's going down. So they somewhat cancel each other out because they're multiplying. And so, okay, you made one number a bit bigger, one number a bit smaller. It is actually going to cancel out a little bit, but not exactly. And so this one is actually ambiguous. Like we don't know, is it an underestimate or an overestimate? Because we don't know which one's going to win out. Like one of them is making the value bigger, the other one's making it smaller. Which one's going to win? Is the overall answer going to be slightly bigger, or is it going to be slightly less than what the true answer is? We don't know. So this is how we can kind of like assess our rounding and our estimations and get an idea of is it overestimation or underestimation? There might be some cases like in real life scenarios where you might want to err on the side of underestimation or err on the side of overestimation, depending on what's more important, like what do you want to avoid more, and so on and so forth. So this is something that's really good to be aware of when estimating. Right, so let's look at a trickier case. Let's say with inverse operations. So division being the inverse of multiplication, subtraction being the inverse of addition. So you say if you have something like this, we can do the same thing again, where we round each of the numbers. You see this is going to be approximately 24 over 30. And I forgot to mention here, you see the little wavy equal sign. That basically means approximately equal to. So it's not exactly equal, but approximately, because we've rounded, haven't we? So it's not exactly. Um, the next one here, again, same thing. We can round each of the numbers and get an approximation. It'd be a little bit simpler. And even with a much more complicated one here, where we've got multiplication on the top and bottom of a fraction, you see those two top numbers will both round down to 15, and 15 times 15 is 225. The bottom one will round to 20 times 18, which is 360, and then we simplify our fractions as always. We get this fraction. Right, and we want to compare, are these overestimations, underestimations? How accurate are they? The first one, we can see the top number is being rounded down and the bottom number is being rounded up. And so what we saw before, that resulted in an ambiguous answer, but that was for multiplication. So you've got to be mindful of the operation that's going on here. Here, it's a division. So think about it. That numerator, if you make the numerator smaller, you're making the overall fraction smaller. But if you take the number on the bottom and you're making it bigger, well, you're now dividing by a bigger number. So the overall fraction is now going to become smaller as a result because you're dividing by a bigger number. So you see, both of those roundings are having the effect of making the fraction smaller. And so the overall answer is going to be an underestimate. We know this is, 4/5 is going to be less than the true value of this fraction. And we can do the same thing with this subtraction. You see, the first number rounds up, the second number rounds down, and this will be an overestimate because the first number being rounded up, so you're making the calculation bigger, but then you're subtracting a number that has been rounded down. So you're now subtracting a number that is a bit smaller. And so if you subtract a slightly smaller number, the overall calculation is going to be bigger. And so that's why this becomes an overestimation. Both of those roundings are having the effect of increasing the value of this calculation. And then you see this final one, we can take each numerator and denominator individually. So the numerator, we can see they're both rounding down. And we saw when multiplying two numbers that are both slightly smaller, the overall thing is going to be smaller. And then on the denominator, two numbers are both being rounded down. And so that overall calculation is going to be smaller. And so now we can look at the fraction as a whole. So you can gradually bring it all together. And you see the top number is being made a bit smaller. The bottom number is being made a bit smaller, which is going to have the effect of making the overall calculation bigger. So the numerator is making the calculation smaller. The denominator is making it a little bit bigger. Again, it's kind of cancelling out a bit. It's going to be ambiguous. We don't know which one's going to win out. Is it going to be overall bigger or smaller? We don't know. So it depends on the calculations. If you hit into an ambiguity at some point, you can't really know for sure which way it's going to go. But sometimes when they do align, you can see is it going to be an overestimate or underestimate. It's a really useful thing to be able to do. And we'll see almost like the reverse way of doing this in the next section on error bounds. So error bounds, when you've rounded something, you're going to have something known as an error bound. Like there's going to be a range of possible values. Like if you've got a particular value, but that's value has come from a rounding, there's a little range of values that would round to that particular value. And we'll see, okay, how do we deal with that? So let me give you an example here. So say we've got a football pitch like this, and we've got the dimensions of the football pitch, 92 meters by 125 meters. And we want to calculate the area of this football pitch. Maybe, we're trying to check that it meets configurations or regulations or whatever. Maybe we need to uh, sow some new grass for this, and we need to know how much the area is so that we can put that grass down. So we calculate our area like this. For a rectangle, it's just going to be simply the two side lengths multiplied together, and we get the area of 11,500 meters squared. Great. Oh, what about if we was then told that these two lengths are not exact? Like these have been rounded to the nearest meter, like the person who measured them. And then, so it's not exactly 125 meters. So that length is not 125 meters, it's 125 meters plus or minus a half meter, which produces this little error range. So can you see between 124.5 and 125.5, not including 125.5, of course, because that would round up to 126, but anything less than that, but greater than 124.5, that all those numbers would round to 125. So, like if you rounded to the nearest whole number. So we don't know exactly what the true value is, but we know it's going to be somewhere in that little range. And same thing with the width. If that one's also measured to the nearest meter, you're going to be off by give or take half a meter. Um, so we get this little range between 91.5 and up to 92.5. Um, it could be any value within there. And so, right, if we want to work out what is the error bounds on that area, particularly the upper bound, so we can see what is the maximum possible area this could have. It's to ensure that we buy, say, enough grass or whatever if we're trying to, you know, green this field. So we could look at the area bounds of the area. And so this here would be an example of the lower bound for the area. So you see what we do is we take because it's area is a multiplication here. So what we do is we take the lower value of the width and the lower value of the length. And if we're taking the lower value of each of them and we're multiplying them together, well, it's going to produce the lower value for the area. And similarly, if we take the upper bound of each of the length and the width, multiply them together, it will get the upper bound for the area. And so we get an error bound for the area is this. So we can see that the area, even though we measured it, calculated as 11,500, taking into account these errors due to rounding, the true value could be as much as, what, 108 square meters off. Like over 100 square meters off. So that's an area of what, 10 by 10 meters. It's quite a significant amount just from slight rounding. So that's the importance of rounding and knowing how you've rounded, and it gives you the limitations of your calculations. How accurate are they? So say if we wanted to green this field, we would want to buy enough to cover 11,608.75 meters squared to definitely be sure it's going to cover the whole thing. Otherwise, we might be a little bit short. Let's take another example. Let's say we have one of the athletes who runs the length of this field. So they run from one length all the way over to the other side, and it takes them 15.4 seconds. And we want to calculate what is their average speed there. Well, we take the distance. Speed is distance over time, isn't it? So we take the distance of 125 meters. We divide it by the time of 15.4 seconds, and we get 8.12 meters per second. Now, say for their team, the record speed that anyone has run is this, and it was measured with a higher degree of accuracy. So, like you see, they've got 4 decimal places here. Maybe this was part of some bigger event where they had better equipment to measure it. And the athlete that ran this distance in 15.4 seconds, they're saying, you know what, I think I actually beat that record. I think it's just the rounding. Because of the rounding, it's now come out to a smaller value than where it should be. Okay, and we want to work out, is there any possible chance that that is true? How could we work that out? Well, we could look again at the error bounds, find out. So we measured it, we've calculated it as 8.12. We know there could, there's an error bound associated to that. So we've got to find out what that is. So again, the length, same as before, because it's rounded to the nearest meter, we've got this little round error bound on the length. And time, our time has been measured to the nearest decimal place, 1 decimal place. So we're off by 0.05 seconds, plus or minus 0.05 seconds, or you can see it as the error bound, whichever one is simpler to you, whatever one makes the most sense. You draw it right as a little error bound with the brackets, or with the little plus or minus sign there. You can see anything between 15.35 up to 15.45 would round to 15.4. So those are our error bounds. Let's take a look first at what is going to be the lower bound of the speed. So again, it's like before, we're dealing with division now, so we need to be careful. If we want the lower bound of the speed, which is distance over time, okay, we take the smaller distance, but we divide by the bigger time. And you see, that's going to overall, it's going to make the calculation smaller because you're dividing by a bigger number. So so you don't just simply take the smaller one of each. You take the smaller one of the numerator, bigger one of the denominator. And you see that gets you a lower bound. And then with the upper bound, we're kind of doing the reverse. We take the bigger value for the distance and the smaller value at the time. So we're dividing by a smaller number, making the overall fraction bigger. And so we get this range for the speed. And you can see that he perhaps could have been running as fast as 8.18 meters per second, which would have been a record. And so, no, what the person's saying is that it is potentially true. They might have actually beaten the record and they don't know just because of the rounding. Um, and you could even go as far as to calculate that he had about a 22% chance of having beaten that record. We haven't done anything on probability yet, but anyone, if you're quite confident with your probability, you might want to try and have a go at that and see if you can work out where that number would have come from, how you would have calculated that based on this information. So, right, let's leave it there today for estimation. So, here you go. Let's end on this. Did you know that actually extremely accurate measurements can sometimes still lead to very large error bounds, certainly over time? Um, so in some situations, yeah, very small errors can blow up to massive errors over time. And this is an example of something known as chaos theory. If you decide to go on to do mathematics or physics at a higher level, like university level, certainly, you'll probably encounter chaos theory. Quite a challenging subject, to be honest. One such field of study is meteorology, which is the study of weather. You might have noticed that you can, the weather forecast never goes any more than a few days in advance. Like even a few weeks in advance is not very accurate. And that's because of this. Like even very small errors in our measurements of the weather can lead to very big errors over time. And I've got like a little example of this here. Like imagine this line going along and it's very stable, very stable. It's staying where it is. And then over time, it gradually starts going all over the place and becomes very, very inaccurate. That's kind of like an example of chaos theory where things can be, they might be very stable over a while. And then these small areas start to grow and grow. So this is one example of a field of mathematics where error bounds and accuracy of measurements is critically important to be, as accurate as you can. So leave it there. Here's your takeaways for today. Um, as always, check the checklist. Make sure you've got all the key points that you understand before moving on. Next time, we're going to be looking at our last topic or topics in numbers, which is about prime numbers, which are like the building blocks of all numbers, and prime factorization, how we can use that. And then that's it. After that, we'll be moving on to a completely new topic. So, right, but prime numbers first. I'll see you there in the next lesson.